Welcome back to RE07. If you're an electrical engineering student or a junior consultant, you've likely faced the classic power puzzle. Sizing a 3-phase cable for a long industrial run. Imagine this scenario. A 45 kilowatts water pump at a remote facility is connected to a substation 200 meters away. You do the math, select a 25 square millimeter cable, and install it. But when you flip the switch, the motor growls, overheats, and won't start. Why? Because you forgot to account for voltage drop. You might have 400 V at the source, but only 370 V at the load. In my 20-plus years of experience in 22 kilovolt substations, I've seen undersized cables lead to motor burnout, premature VCB tripping, and catastrophic heat failures. Today, we are moving beyond manual lookup tables. We are going to build a decision support tool in Python that not only calculates voltage drop, but automatically selects the most cost-effective and safe cable size based on IEC and NEC standards. Today, we aren't just looking at the code. We are looking at the data that drives the code. If you are a student preparing for your FE exam in the States, or your chartership in the UK, you know that a single misplaced decimal point in your inputs can lead to an undersized cable that melts inside a conduit. Today, I'm going to walk you through the 5 critical input parameters our Python script requires to size a cable for an industrial motor or a 22 kilovolt substation feeder. We're going to talk about why we use these specific numbers and how they change depending on whether you're in North America or Europe. The first thing our script asks for is system voltage. In the UK and Europe, we typically operate on a 400 V or 415 V 3-phase standard. In the USA, you'll often see 480 V for industrial applications. Why does this matter? Because a higher voltage means lower current for the same amount of work. Next is load power. We usually input this in kilowatts kW. In the field, you'll look at the nameplate of the motor. But remember, this is the rated power. As a safety officer, I always advise my students to check if the motor has a service factor. If a motor is rated for 45 kilowatts but has a 1.15 service factor, it can actually pull more current. Our input must reflect the absolute maximum the cable will ever see. The third input is the power factor. This is the one that confuses students the most. Think of it as the efficiency of the electrical phase. If you have a purely resistive load, like a heater, your power factor is 1, but industrial plants are full of induction motors. These motors create magnetic fields, which causes the current to lag behind the voltage. Typically, we use an input of 0.8 to 0.85. If you enter one for a motor load, your Python script will tell you that a 16 square millimeter cable is fine. But in reality, the lagging current is much higher, and that cable will get hot. In our script, we treat the power factor as a safety constraint. Never guess this value. Check the motor datasheet. Finally, we have the maximum allowed voltage drop. Most international standards, including BS 7671 UK and NEC USA, recommend a limit. 3% for lighting, because lights flicker or dim if voltage drops. 5% for power motors, because motors lose torque and run hot if voltage is too low. As a safety officer, I tell my students, just because the code allows 5% doesn't mean you should aim for it. If I'm designing a critical cooling pump for a substation, I might set my input threshold at 3% to provide a buffer for future expansion or extreme heat conditions. Your Python script gives you the power to simulate these what-if scenarios in seconds. You can give your students this template to copy and paste. It ensures the AI writes code that is technically accurate and project-ready. Engineers, AI is a powerful tool, but it doesn't have a license you do. Always verify the output against your manual calculations once. Use AI to do the heavy lifting of the math, so you can focus on the high-level design and safety of the substation. Now, let's put the theory into practice. Watch the screen. We are looking at a real-world industrial scenario. a 45 kilowatts motor located 150 meters from our 22 kilovolt substation. Traditionally, you'd be flipping through cable manufacturer catalogs and tapping a calculator for 10 minutes. Watch how Python changes the game. First, we input our system voltage 400 V. Next, our load 45 kilowatts. Now, notice the power factor. I'm entering 0.85. This is where most students fail. They forget the lagging current, but our script is ready for it. Finally, we set our distance to 150 meters and our safety threshold to a strict 5% voltage drop. In the background, the selection loop we coded is testing every standard cable size in our database. It rejected 16 square millimeter. It rejected 25 millimeter. The voltage drop was too high. It's searching for the sweet spot, the smallest cable that is both safe and cost-effective. This is the power of the hybrid engineer. By letting AI and Python handle the repetitive math, you eliminate human error and free yourself up to focus on high-level system safety. If you want to build your own engineering toolbox like this, the source code is linked in the description below. Download it, test it, and start automating your workflow today. I'm RE7. Stay safe, code with precision, and I'll see you in the next masterclass.